Alright, so we will continue with interlude, which is the process API. So the process API is the API that is being invoked by your process to tap into the kernel. So we will discuss that in this chapter. In this interlude, we discuss process creation in Unix systems. Unix presents one of the most intriguing ways to create a new process with a pair of system calls, fork and exec. So this is a new way. The one of the most inventive characteristics or API of Unix is the invention of this pair, fork, and exec, and we will discuss that further. A third routine, wait, can be used by a process wishing to wait for a process it has created to complete. We now present these interfaces in more details with a few simple examples to motivate us, and thus our problem. How to create and control processes. What interfaces should the OS present for process creation and control? So what interfaces should the OS present for process creation, and how does it control that when it allocates virtual memory, the state, the registers, etc.? How should these interfaces be designed to enable powerful functionality, ease of use, and high performance? Again, the main job of the OS is to make it easy to use. So we will gonna discuss that. So a lot of these are abstracted by the OS, even this one node that we are using. So the fork system call is used to create a new process. So here we have a fork. More specifically, you have a running program whose code looks like what you see in figure 5.1. Examine the code, or better yet, type it in and run it yourself. Well, okay, we admit that we don't know that for sure, right? Who knows what routines you call when no one is looking? But fork is pretty odd, no matter how unusual your routine calling patterns are. So these are one of the most important concepts of API that allows our modern operating systems, because this fork allows us to create a copy of a child. Imagine this like copying the shell with the same virtual memory states, etc. if we initiate this fork. So we know that shell actually allocate a memory, but now we will refine that notion. Shell actually allocate a memory, but not just but when it invoke this fork system API, it actually copy that memory it allocated initially from the shell and create similar, like it's almost the same, copy alongside it. So it has a different memory. It doesn't override the previous virtual memory. Okay, and also those memory was mapped using page table to its actual physical address, but basically it's managed by the OS as well. So here are example of calling fork p1.c. So when you run called p1.c, you'll see the following. So hello, PID 29146, parent of, and then parent of 29147, PID 29146, child PID 29147, then prompt. So you can see we invoke /p1. Let's understand what happened in more detail in p1.c. When it first started running, the process prints out a hello message. Included in that message is its process identifier, also known as PID. So When we first run that, it prints out a hello message. Included in that message is a process identifier, because what happens is that we have this shell. It copies that using this fork, and then this fork has its another PID, or identity or process ID. That's why, as you can see, prompt hello PID 29146, parent of 29147 is PID 29146, and child is 29147. So we created a child, and we see the parent of that child. So just because we copy the same memory, the same allocation of memory from the shell, which is this prompt, does not mean it's also the same PID, because this process ID are dynamically allocated by the process by the operating system whenever it allocates a new process to track that process. Remember the structure. So those structures are use this PID to track this process as well, to be able to better manage it for ease of use of this different program. Now included in that message is its process identifier, also known as PID. The process has a PID of 29146. In Unix systems, the PID is used to name the process if one wants to do something with the process, such as, for example, stop it from running. So we can send a signal from it. So we can do a lot of things if we know its process ID. So it's used to name it for us to be able to control its states. So remember, not the process is not just a code; it also a memory, the register, its states, etc. This is a more detailed notion of that. The process calls the fork system call, which the OS provides as a way to create a new process. So fork is provided by Unix as a way to create a new process, kind of like copying it, or almost the same, right? The odd part, the process that is created is an almost exact copy of the calling process. So that is the odd part, because if we are running a shell, if we call a fork, it will mimic those who called from those who called it. In this case, the shell, right? So depending on who called it, it will mimic that. So that's what the call is for. That means that the OS, it now looks like there are two copies of the program P1 running, and both are about to return from the fork system call. So it looks like there's two copies of the program P1 running, but in reality, it's just a two process with two virtual memory alongside it. It's just almost the same copy. So the newly created process called the child, in contrast to the creating parent, doesn't start running at main like you might expect. Note the hello message only got printed out once. So the child doesn't start running at main, unlike the parent. The hello message only got printed out once. Rather, it just comes into life as if it had called fork itself. So it doesn't come into life just like a parent invoke main, but it's just kind of a copy of the parent. So just like a child will not be there without a parent, but a parent could be there without the child because that's not his parent. It's the same here. It just comes to life as if it had called fork. Okay, so you might have noticed the child isn't an exact copy, especially through it now has its own copy of the address space, its own private memory. So like I said, it has a own private virtual memory. It has a copy of the address space. It also has its own registers, its own PC, and so forth. the value it returns to the caller of fork is different. So it has its own memory, right? It also has its own register because the CPU has to track this process in some way for it to go back to it in case it needs to left, just like what we've discussed in the registers in the previous video. Specifically, while the parent receives the PID of the newly created child, the child receives a return code of 0. So again, specifically, while the parent receives the PID of the newly created child, the child receives a return code of 0. So the parent receives the PID of his child because he's the one who created it. While the child itself doesn't create another child, so it returns 0, meaning it's successful. This differentiation is useful because it is simple then to write the code that handles the two different cases as below. As this, so it handles two different cases. First, fork failed, exit, then else if, new process, child new process, and then parent goes down this path. So as you can see below, it handles two different cases. Now you might have noticed the output of P1.c is not deterministic. When the child process is created, there are now two active processes in the system that we care about, the parent and the child. So here is the another example, the example that we have earlier. So assuming we are running on a system with a single CPU for simplicity, then either the child or the parent might run at that point. In our example above, the parent did and does print out its message first. In other case, the opposite might happen as we shown in these output trees. So here, the child comes first before the parent. So why is that? This is the wait or the wait system API will come into existence. So the CPU scheduler, a topic we will discuss in great detail soon, determines which process runs at a given moment in time. Again, CPU scheduler. It's not OS scheduler. So this determine which process runs at a given point in time. Because the scheduler is complex, we cannot usually make a strong assumptions about what it will choose to do, and hence which process will run first. This non-determinism, as it turns out, leads to some interesting problems, particularly in multi-threaded programs. So if you have the multi-threaded, just like the program we have before, we'll see a lot more problem with this non-determinism of CPU schedulers. So hence we will see a lot more non-determinism when we study concurrency in the second part of the course. So we will tackle that moving forward. But one of the ways to we tackle that is using the wait API. So far we haven't done much. Just created a child that prints out a message and exit. Sometimes, as it turns out, it's quite useful for a child process to finish what it has been doing. So sometimes your parent needs to wait you before it completes. So this task is accomplished with the wait system call, or its more complete sibling wait PID. So this with more complete sibling is another system call, which is wait PID, which has more configuration or more detail function. In this example, P2C, the parent process, calls wait to delay its execution until the child finishes executing. When the child is done, wait returns to the parent. Adding a wait call to the code above makes the output deterministic. Can you see why? Go ahead, think about it. So here, P2, hello child, parent of 296. So as you can see, the parent waited for the child to complete, and here's the code: calling fork. So we call fork. If fork failed, exit. Then child new process, and then parent goes down this path, and then return. So with this code, we now know that the child will always print first. Why do we know that? Well, it might simply run first as before, and thus print before the parent. However, if the parent does happen to run first, it will immediately call wait. So where is wait here? Here. Wait, null. So if the parent runs first, it will immediately call wait. However, it it could simply run first as before, thus print before the parent. But if the parent runs first, with it's usually B, because this is the one that creates this process. The child copy its process or its configuration from the parent. This system call won't return until the child run and exited. So the child needs to exit first before the parent exits. Thus, even when the parent runs first, it politely waits for the child to finish. That's why we have this: hello, child, and then parent. However, if thus, even when the parent runs first, it politely waits for the child to finish running. Then wait, returns, and then parent prints its message. So after the child exits, it politely waits for that exit. The parent politely waits for that exit. Then wait will returns to the parent, and then parent prints its message. That's why it's show the child name first, which is the PID, and then the parent. So instead of the parent first and the child, it is child and then the parent. And a final important piece of the process creation API is the exec system call. So this system call is useful when you want to run a program that is different from the calling program. So since the child is being copied from the parent, if you want then to run a code that's completely different from the parent, this is where the exec will come. So these are one of the fundamental system API created by Unix. So for example, calling fork in p2.c is only useful if you want to keep running copies of the same program. On Linux, there are 6 variants of exec. Exec L, exec LP, exec Y, exec VP, and exec VPE. However, often you want to run a different program. Exec does just that. So there's a lot of available system calls with a slightly different configuration and more detailed function available in Linux for exec. But here, we will just gonna discuss how it makes the calling program different. So here, calling fork, wait, and exec. So in this example, the child process calls exec VP in order to run the program WC, which is the word counting program. In fact, it runs WC on the source file p3.c, thus telling us how many lines, words, and bytes are found in the file. So here's how it works. So we execute ./p3 on the shell. The shell will initially fork its own version, and then that own version that he created as a child will now call exec VP, and then exec VP will call WC, which WC is actually a binary available from most current Unix systems, and thus this WC is converted to binary data loaded into memory, and then calculate what logic it asks for from that from the CPU, from the binary data it loaded to the virtual memory. So that's how it works in details, but we will gonna further refine that notion. So the fork system call is strange. Its partner in crime, exec, is not so normal either. So these are actually partner in crime. So as you can see, this combination of fork, wait, and exec with P3.C, as you notice, we have hello child parents because we use wait, and then in this wait, before wait, we ask that to run word count. So before you wait for the parent, you run the word count. So here you create a child new process. If it failed, exit program WC input file. So arg p3.c, the same file is your input, and then my args null. So mark end of the array. So these my args are actually the OS way of accepting input strings from your code. So it's kind of like high level, but yes, it's a lot. Before your OS allocate memory, it asks for that string like this arg or char argv. It's also part of your code. So the fork system call is strange. Its partner in crime, exec, is not so normal either. What it does, given the name of an executable like WC, so WC is an executable, and some arguments p3.c, it loads code and static data from that executable WC. Usually it's in, I think, /bin folder of your Unix, from that executable, and overwrite its current code segment. So it overrides that current code segment and current static data with it. So this is an override. What happens is that this WC, instead of this exec VP, instead of just copying the parent program, it actually overwrites that entire program and replace it with its current code segment. It got from its binary data WC from /bin to be executed now on that memory. So all of the rules and also the current static data. So all of the rules that we've mentioned here earlier, such as, where is that? So here, since before it's an almost exact copy of the parent process, that means to the OS, it now looks there are two copies of program P1 running, and both are about to return fork system. The newly created process called the child, in contrast to the creating parent, doesn't start running at main like you would expect, right? You might have noticed the child is an exact copy, specifically, although it has its own copy of address space, its own private memory. Yeah, here the private virtual memory and its own registers, its own PC, and so forth, and the value returned to the caller will now replace by this. So it overwrites this exec VP and the WC on that special or private memory. Then the heap and stack and other parts of the memory space of the program are reinitialized. So again, those stack, the size of the memory, the return address will be changed by this arg that you mentioned. And then the initial instruction pointer, the main, etc. Then the OS simply runs the program, passing in any arguments as the arg of that process. So the OS simply accepts that parameter that you put here, in this case the p3.c in the first argument of myargs, and mark end of the array, and then runs word count exec vp myarg. So OS simply replace those arguments into that initial private memory. Thus, it does not create a new process. Rather, it transform, that's the key, the currently running program, formerly P3, into a different running program, WC. So that's how you create a replicate to a completely new process, or transform process. So after the exec in the child, it's almost as if p3.c never ran. A successful call to exec never returns. So p3.c it's almost look like the p3.c never runs. You just kind of like use that as a starting point, but you entirely redefine that replica to call your function, which is in this case the WC, from using the OS. And then it never returns because it doesn't need to, since it's not a child of that parent anymore. It's not an exact copy that requires you to return something. It's a completely different program. You just need that as a tool to or as a initial program, but you plan to completely change what you want, basically, like completely transform that virtual memory, the registers, the PC, the value, etc. So the stock as well will be changed, the return address, the instruction pointer in the register. So we will refine that in details as we move on the next chapter. So of course, one big questions you might have: why would we build such an add interface to what should be the simple act of creating a new process? Well, as it turns out, the separation of fork and exec is essential in building a Unix shell, because it lets the shell run code after the call to fork, but before the call to exec. So again, because it lets the shell run code after the call to fork, but before the call to exec. So we run first. So it allows the shell to run code after the fork, but before the exec. So as you can see, we can run code, right? Once we create a copy on that p3.c that we created before we execute the exec vp. So the shell is just a user program. So it's still a user program in user mode. It's just a C program created by you, a programmer. It shows you a prompt and then waits for you to type something into it. You then type a command like the name of an executable program plus any arguments into it, like the WC, or in that code WC, myargs WC, and the p3.c. So those are the arguments and the code. In most cases, the shell then figures out where in the file system the executable resides. It calls fork to create a new child process to run the program. So in most cases, the shell will figure out where in the file system where that executable resides, such as the WC and that p3.c, and it calls fork initially to create a new child process to run the command. But then that child process with that own virtual memory will be transformed, as like what I've said. Then it calls some variant of exec to run the command, and then waits for the command to complete by calling wait. So we can also use wait if we need to wait for that command. When the child completes, the shell returns from wait and prints out a prompt again for your next command. So when the child completes, the shell returns from wait and prints out a prompt again, ready for your next command. So once the child completes there, the shell will return from wait, because this is how the program was structured, and then it will print out a prompt again asking for the shell ready for the next command. So that's how the shell are programmed. So it's just as a program that allows you to input a command or a system call to the operating system. So as you can see, in order for you to really use a program such as this command line as simple as a shell, you need two programs, or three actually. You need you need three API, two programs rather. You need the shell program and you need the p3.c program. And those shell program are program in such a way that after that command or a program like p3.c that you invoke, um, that also call a system call like fork and exec vp as well as wait, and after that wait is invoked, the shell program will return to the prompt. So as you can see, you have this initial program that allows you to spawn a copy of another program, which in turns allows you to also transform that program using exec vp or a transformation to trap into kernel. So basically, that's the magic of the Unix. The Unix allows you to do that transformation. It allows you to combine those different commands in this well-designed operating system. So that's how you create this, multiple transformation and complicated task in GUI or in command line before. So here, and there are lots of shells, TCSH, Bash, and ZSH to name a few. So this shell is fundamentals in programming because this is how you type commands into your development environment. This is the program that create a shell that spawn that could transform to another program that you can use to change your code. So you should pick one, read its man pages, and learn more about it. All Unix experts do. So you should read these man pages of these shells, because this is the key in invoking these multiple programs and then tapping into the kernel or of the OS. As you can see, we use C, which in this case the fork, exec vp, as well as wait. So one of the fundamentals API we use using shell to trap into the kernel. So the separation of fork and exec allows the shell to do a whole bunch of useful things rather easily. So this combination of this shell of fork and then fork and exec allow the shell to do a bunch of useful things rather easily. For example, this. So it allows to do this creative transformation because of this combination of multiple programs as well as how the operating systems were designed. So again, the file system, all the programs has access to file system. So therefore, we can redirect the output such as this. You have this shell program prompt will execute this copy of wcp3.c, and then this will transform to completely different virtual memory and registers, and then it will transfer the result in this new file.txt. So in the example above, the output of the program wc is redirected into the output file, the new file.txt. The greater than sign is how said redirection is indicated. So shell or this operating system using this output or greater than shell is very powerful because this what allows the shell or the OS to redirect the output of this p3.c, counting the p3.c into the new file.txt. So the way the shell accomplishes this task is quite simple. So when the child is created, before calling exec, the shell, specifically the code executed in the child process, closes standard output. So before calling exec, this is how you conduct code after the fork and before the exec. So it closes the standard output of the fork or the child process and opens the new file .txt. That's before calling exec. So the shell, specifically the code executed in the child process, closes standard output and opens the file new file.txt. By doing so, any output from the soon-to-be running program wc is sent to the file instead of the screen of the shell. Open file descriptors are kept open across the exec call, thus enabling this behavior. So the open file descriptors, which is the system call for open file. Again, the file system allow you to access this file for different programs, such as in this case exec. So or p3.c that has exec, a new program created by p3.c using WC. This is an entirely new program, but in this p3.c it has exec vp, right? That initiate a WC. Where's the p3.c? Here. So as you can see, we create a fork there. So it is a completely different program. So any output from the soon-to-be running program is sent to the file instead of the screen. So usually this prompt, this shell, that open file descriptor that you put into it as a command could be represented in this screen if you meant to output that. But this is not what this file or this code are saying. This saying is that whatever this program does, its output is transformed into or copied or transformed or put into new file.txt. It's sent to the file instead of the screen. Open file descriptors are kept open across the exec call. So across the exec call, again, those open file descriptions, since there's also an open here. As you can see, it's a system call as well. Where's that open file descriptor? Input file mark and run words count else. So that open file descriptor, probably this greater than. So how said redirection is indicated, thus enabling this behavior. So here is the step-by-step process of how it actually works. So first, shell passes command wcp3.c to new file.txt, and then shell fork inside the code. Shell fork or create a child process. Kernel create child PCB. So the child PCB that we discussed in the previous chapter, that track does process created in order for us to manage a state and what do you call this, OS CPU scheduler to determine which program to run. If this PCB are used for that, duplicates FD tables. So it duplicates the FD table from the parent. That's why it allows them to open that file, because this FD, like file description, allows that operating system to access the file by multiple programs. And then it set up CW page tables. So the page tables is what maps your virtual memory to physical memory. So it creates that virtual memory alongside with the parent. So that's what fork does. In child, shell does close one and open new file.txt. So as you can see, in child, where's that? Okay, so in child shell does close one. So because we are able to execute the code after the code, we close that code, and then we open a new file that's code. So that's a system call that the redirection greater than, a simple greater than does. So kernel updates child's FD table. So FD1 is file object for new file.txt. So meaning we will redirect the output now to new file.txt instead of the screen. Now child calls exec ve and then /bin/wc. So this is where the wc binary goes in a /bin folder on your operating system, and then it has argv and then env. So that's a system call created by this child in the inside of our code, and then kernel loads slash bin slash wc into new virtual address space. So it actually the OS actually loads that into a new virtual address space. So it transform it instead of just um, same virtual address. So just use that initial fork process to spawn this new virtual address that we will allocate now for the child. So since we use this arg, right, as a initial way for the OS to create the stock pointers, which are used for the function local variables, and then instruction pointer to then sets the IP to start, right, for this program to start. So virtual address space and set IP to start, and SP with arg slash argv. FD table is preserved. So since FD table is preserved, you still have access to the file. Now WC runs and writes to FD1. WC will run now and will write to FD1, which is kernel route writes to the file object. So file receives output. So the kernel now will route this FD1. Remember, the kernel are so malicious or so careful in providing this disk access. So this is how the kernel runs that in details. There's a lot of steps. So this is the only time, which is the fifth step, this WC runs and writes to the actual FD1. It doesn't until this the OS, or until this time, that it actually writes to the new file.txt, the result of counting those p3.c. So after WC exits, kernel wakes parent shell. So as you can see, in this OS are actually in the memory already. So if you're in memory, it means you're running. You're not a static code anymore, the one we created. So it's actually loaded already. So we actually see that in creating this new virtual process, and then WC running, So since it's already loaded in the code, so first we allocate it, right? And then WC run and writes to FD1. That's where the kernel run or put the WC. Where's that? Here's where it calls the WC first, right? So it doesn't run that. So there's a call first, and then allocating it, and then setting up the arg and env for the stock pointer and instruction pointer. Now kernel loads it. So it loads first /bin /wc into new virtual address to make that loaded data stuck in WC comes alive space, and set IP to start, and SP with argc/argv. So it set that WC to start, so that program will start, because again, start_start is what invoked the main of the program, and that's instruction pointer will also determine what instruction to be done next, and then that's will exit that, and this SP with argv along with IP is what will return the address after the process has been done. Now WC run and writes to the actual new file, that's text, using its preserve power to F, which is FD1. So kernel writes to the file object. So file receives output. So now the kernel writes to the file object. So this kernel actually working in disk mode already, because we have trapped into the kernel now. The OS is now talking to the IO, or this file syntax that allows it to write the file object, so that it outputs it on the new file.txt. So after WC exits, kernel wakes parent shell, which was wait. So after it exits, it wakes up the parent shell, which was wait, and shell prints a new prompt. So before, the parent is actually on IO mode, which is the blocking state we've discussed in the previous video. And then After the W exits, the kernel wakes parent shell, which was waiting. So the kernel, the OS, wakes up the parent. It's done now, and then now after the IO is done, the shell prints a new prompt. So until the WC has been write as a file object into the actual disk, then the only time the parent shell will actually print a new prompt. So that's the shell program we're designed after that IO. So it's pretty intricate details, but it's so useful. Figure 5.4, which is this, shows a program that does exactly this. The reason this redirection works is due to an assumption about how the operating system manages file descriptors. Specifically, Unix systems start looking for free file descriptors at 0. In this case, stdout file no will be the first available one, and thus get assigned when open is called. Subsequent writes by the child process to the standard output file descriptor, for example, by routines such as printf, will then be routed transparently to the newly opened file instead of the screen. So here's the output of running the p4.c program. So again, specifically, Unix systems start looking for free file descriptors. That's the reason at 0. So that's the reason why this Unix system works, such as fork, exec, vp, wait. In this case, stdout file no will be the first available one, which is the file descriptor 0, and thus get assigned when open is called. So the fd0 or the stdout file no will be assigned when open is called. Subsequently, writes by the child process to the standard output file description, for example by routines such as print, will then be routed transparently to the newly opened file instead of the screen. So since the child process to the standard output file description, for example by routines such as printf, will then routed transparently to the newly open file instead of the screen. So since it started at 0, which is the first one, which automatically on the screen, and then since it opens a 1, a file, which is the next one, those will be routed to that file. So that's the reason why it's worked, because this Unix system start, or the OS starts at 0 and then look at the next one, which is in this case the newly opened file. That's why it routed the output to that newly opened file. So here's the output of running p4.c program. So that /p4 cat p4.output 32.109.846.p4.c. So Unix pipes are implemented in similar way, but with the pipe system call. So there's also a pipe system call. The output of one process is connected to an in-kernel pipe like Q, and the input of another process is connected to the same pipe. Thus, the output of one process seamlessly is used as input to the next, and long useful chains of command can be strung together. So these pipe are also, a pipe system call are implemented in similar way as fork and exec vp. So, however, in this case, actually one process is connected to an in-kernel pipe like Q, and the input of another process is connected to the same pipe. So the input of another process is connected to the same pipe. Thus, the output of one process is connected to the other, right? Kind of like the greater than symbol. So as a simple example, consider looking for a word in a file and then counting how many times said word occurs. With pipes and the utilities grep and wc, it's easy just to type grep-0 foo file and then vertical line wc-l into the command prompt and marvel at the result. Finally, we just sketch out the process API at a high level. So that's the high level of process API. Again, we will gonna refine this notion as we move forward. So finally, we have just sketched out the process API at a high level. There's a lot more detail about these calls out there to be learned and digested. We'll learn more, for example, about the file descriptors when we talk about file systems in the third part of the book. So we will learn more about the FD and how it preserve that file access across programs when we talk about systems, file systems in the third part of the book. For now, suffice it to say that fork/exec combination is a powerful way to create and manipulate process. So here, all of the above with redirection. So process control and users. So beyond fork, exec, and wait, there are a lot of other interfaces interacting with processes in Unix systems. For example, the kill system call is used to send signal to a process, including directives to pause, die, and other directives to pause, die, and other useful imperatives. So a kill system call is actually used to pause as well, not just to die and other useful imperatives. So again, just like an exec VP, there's a lot of could be a lot of implementation of this system call. Just like in Linux, there's a 6 implementation of exec VE. For convenience, in most Unix shells, certain keystrokes combination are configured to deliver a specific signal to the currently running process. For example, Control C sends a SIGINT interrupt to the process. So sometimes a keyboard as well became a shortcut because those are most useful signals, such as the Control C. It sends a SIGINT interrupt to the process, normally terminating it. And Control Z sends a SIG stop signal, thus pausing the process in mid-execution. You can resume it later with a command, and the FG built-in command found in many shells.